So now relationship between angular momentum and moment of inertia. Now when rigid body describes pure rotational motion, its all constituent particles describe circular motion. This is what we had already discussed. And angular momentum of the particles about corresponding centers are. Now how do you write angular momentum? You will write angular momentum is nothing but r cross p, and if there is an, so see, this is the axis about which some particle is, let's say one particle is moving, and now this is having the velocity is tangential, it is perpendicular, this is basically in this horizontal plane, and this is having m mass. So you will write that v is nothing but v equals to r omega. And what about L? L is r cross p, or we can say rp sine theta. So what is r? R is basically this position, right? R is this position, and the theta is angle between this and this vector. So this angle is already 90 degree. So here I'll say it is sine 90 degree. So I can simply write rp. And what is rp? P is nothing but mass into velocity, linear momentum. And what about v? V is nothing but r omega. So r m into v. V is nothing but again r omega. So this gives me m omega square r. So this is how you can write just the magnitude of angular momentum. Now direction of angular momentum, when we talk about, see, if the rotation is, let's say, clockwise or anti-clockwise. If the rotation is clockwise or anti-clockwise, then we can say all the particles will be doing the same kind of motion. All will be either clockwise or all will be anti-clockwise. But so we will say, we can simply add the angular momentum. See, they are vector quantities. But when I need to add the vector quantities which are all having same direction, we needed to directly add the magnitude because direction is already same. So angular momentum of first particle is m1 omega r square. 1 second, this is r square. So m omega r square. So m1 omega r square. I should write omega 1. But I know that omega of all the particle is nothing but same, which is the angular velocity of entire object. So omega is same for all. So I am writing mass 1 omega r1 square. Angular momentum of second particle is going to be m2 omega r2 square. Like that, we can write angular momentum of all the particles, and we can add all the angular momentum of all the n particle. Let us say our body is having a small n number of particles, which can be like infinite particles, that is also fine. So we are adding all in small angular momentums to get the total angular momentum. And here if we write that L1, what was L1? L1 was m1 omega r1 square. So m1 r1 square, omega has been taken as common. L2 is m2 omega r2 square, again omega is outside, and like that for all particle we have written, we can take out omega common. And what is there in the bracket? We check the bracket, that is summation of all mi ri square. Isn't that thing is moment of inertia? And this omega is basically I omega. So when we solve this, we get the relationship L equals to I omega. And this is an again important relationship which we need to remember. Now this is again similar to, instead of angular momentum, I am going for linear momentum. Instead of moment of inertia, I am going for normal inertia, that is mass. Instead of omega angular velocity, I am going for velocity. So we know that P is equal to mv, and similar rotational analog is L is equal to I omega. So this is an important relationship. Like all linear to rotational analog, we can make it also. Since P is equal to mv, the L should be equals to I into omega. Now, next is relationship between torque and angular momentum. So, we know that L vector is equal to R cross P. What if I differentiate it? So, I get dl by dt, the differentiation of angular momentum, is equal to, here the R and P both are variables. I'll say I am going to apply UV rule. So since y is equal to u times v, so dy by dx, we can say the differentiation is going to be v times u dash times v plus v dash times u, or u times v dash. So first I am differentiating this. So dr by dt I am keeping it as it is, and then I am differentiating p and I am keeping r vector as it is. So this is the relationship which we get between the once we get the differentiate, then this is the equation what we get. Now next is, what is dl by dt? So here this dr by dt is nothing but my velocity vector, right? The change in position vector with respect to time is velocity vector, and p vector is nothing but mv vector, right? We already know the linear momentum is nothing but m times mass, it is the product of mass and velocity. Then this plus r is r, and dp by dt is nothing but my force vector, r cross f. Now when we do this, here it is basically v vector cross mv vector, and now this m can come out, it is basically v cross v, and the cross product of a vector with itself is always 0, because how do you define a cross b? A cross b is, the magnitude is ab sine theta, where theta is angle between a and b, but what is the angle between v and v? That is 0 degree. So when you get the magnitude, it is v into sine 0 degree, and that is going to give me 0. So this thing is 0, and when we write this thing is 0, and this is r cross f. So here r cross f is what? Now how do we define our force? Our force is nothing but dp by dt. So force is rate of change in linear momentum. Similarly, I can say my torque is rate of change in angular momentum. So this is my net force or external, this is my net force or external force, and this is my net torque or external torque. So external torque is given by r cross f. So this is going to be an important relationship which we can write, and we know that torque is nothing but r cross f. So torque is equal to dl by dt. So like f is dp by dt, we can define our torque to be dl by dt. Rate of change in angular momentum is defined as torque. Now let us talk about the next topic, that is conservation of angular momentum. See, when a linear momentum is conserved, we already talked about the conservation of linear momentum. When our external force is 0, we will say the linear momentum won't change. Similarly, we say that torque is dl by dt, rate of change in angular momentum. So when our external torque is 0, the angular momentum must be a constant, it shouldn't change. So it is similar to F external. If x external is 0, then we say the linear momentum P is a constant. So it is similar that if external torque is 0, then angular momentum must be conserved or angular momentum must remain same. So whenever there is no external torque acting on the body, or we can say system of particles, then we can say that angular momentum must remain the same, or it can be conserved. So we can say in absence of any external torque, the total angular momentum of a system is conserved or is constant.